Good morning, everyone. My name is Jeffrey Townsend. I am Vice President of Engineering in charge of switching products at Big Switch Networks. And I am the primary architect and steward of the Open Network Linux project, which we are going to talk about today. Let's see. What are we talking about? What is Open Network Linux? If you'd like to read my company's marketing blurb, Open Network Linux is an open source foundational platform software layer for next generation modular NOS, blah, 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 blah. It's all true. But really, really, what is it? Like Kurt was up here before, I want to take a room temperature real quick because we have a lot of different kind of people from different backgrounds here. So we are still talking about networking equipment. We're talking about switches and routers. Most of the genesis of this is for top rack switching and data center networking. So what we're talking about now are open networking, switch, and route hardware platforms, right? And Open Network Linux is a Linux distribution designed to run and support development and deployment on those platforms. Doing it's not as easy as you think. If anybody's ever done it before, worked at a company that's worked on a network operating system, worked on a company that's developed software for these platforms, it's really not, it's not for the faint of heart, let's say that. So the first question is, why would we need another distribution for this? Why not use an existing distribution like Ubuntu or, CentOS or Red Hat or something like that, something that you would normally just install on your PC or on your server hardware? And the reason is that switches and routers are, we're trying to make them more like servers as part of OCP, but they're just really not the same. They got some really specialized hardware and some really specialized quirks that make things difficult. So what we do is basically we do base Open Network Linux on an existing Linux distribution. We use Debian, and we add stuff on top to make it possible to install that software using Kurt's ONI to understand the custom peripherals that are on these devices, and to make it, in general, possible for you to abstract away the details of the platform so that you can develop software to do work. By the way, if you have a question, go ahead and raise your hand. They would appreciate it if you could move to one of the microphones or have the microphone handed to you before you ask your question so that it can be recorded. Otherwise, I'll repeat the question for you. And I only have about 30 minutes, and we'll have a breakout session later if you're interested. I'm happy to answer questions during the presentation. I'm happy to answer any questions you have later, whether you attend the breakout session or not. I'll be here all day. Okay. All right. So to understand why all of this stuff is special, we need to talk about what the switch hardware, what this stuff looks like, first of all, and why is it really different from a server that you'd normally, normally be familiar with. So all of these switches, they obviously have a CPU, and they have memory, and they have storage, but the CPUs kind of run the gamut. For a long time, CPUs in these boxes were PowerPC because they were a good price point for performance. But these were all for, companies like Cisco and Juniper and everybody who made their own box. And OCP is actually a big part of the reason why most of these switches are now going to x86, so that a lot of standard server kinds of software can run on those switches. But in general, what you'll find that there's 32-bit and 64-bit PowerPC processors. All of the x86 is, for the most part, 64-bit. And then you have really low-cost solutions that have ARM32, higher performance solutions that have ARM64. And so right out of the gate, you have a bunch of architectures that you normally wouldn't intersect in your normal software development cycle. On top of that, these boxes have a data plane chipset. And these are things that if you're into networking, you'd be more familiar with. So all the chipsets from Broadcom, Trident, Trident 2, Tomahawk, all of these things. And chipsets from other companies, Barefoot, Centec, Cavium, the whole list of people who make switching and routing data plane chips. So these boxes have one or multiple one of these on here. If it's a data center switch, you usually have some variability on the layer 1 connectivity modules. So SFP, QSFP, QSFP28. So these are all pieces of hardware that are made to interchange and stick into these boxes, and they add complexity to how you operate the box. In addition to that, you have some things that you might find on a normal server, but you would never actually have to worry about operating. Things like temperature sensors, fans, power supplies, status LEDs, EEPROMs with identification information, like Kurt was talking about before. And they also have specialized hardware for managing these things. A lot of custom firmware running in programmable logic devices. BMCs are baseboard management controllers that handle making sure the box doesn't catch on fire, stuff like that. And so all of these kind of look the same. They all have the same set of stuff, and then so it sounds like it might be easy. And if you look at what we call a network operating system, something that is actually going to run on one of these devices, it's at the high level, a lot of them look the same. You've got some kind of kernel that needs to run on it. It could be VxWorks, it could be Linux, it could be BSD. Almost everything in open networking now is based on Linux, but you need some kind of kernel to run in the box, and that kernel has to support the architecture that you're talking about. So right there, you're just like, if I've got a ARM32 box and you don't even know what to do with that, you're out of luck. You need some sort of what we call user land. It's basically what you would consider Linux or a Linux distribution to be. So you need to be able to run Bash, you need a shell, you need to be able to run Python in your web server and all that kind of stuff. So the user land is the collection of all of those things that allow you to actually create the operating system. On top of that, specific to a network operating system is you have stuff that runs the control plane and the data plane. So control plane might be you want to use BGP. Data plane might be how do you program a Broadcom chip to do L3 forwarding. So when you get to the point, this is the interesting part of the network operating system, is what do you choose for your networking control plane, and how do you affect that control plane into your data plane. Okay. On top of that, in order to make all that kind of stuff work, you also need other specialized software, especially in a data center, what I would call connectivity management software, so that you can you have these modules. Like if you don't know what an SFP is or a QSFP, I can explain that later. But these are different modules that allow you to connect copper or optical connectivity to your switch to other devices in your network. And there's a whole subset of programming interfaces for these things and standards for recognizing them and operating them. And so you need a lot of software to do that. And that software has very little to do with how you want your network to function and more to do with how your network is physically connected. On top of that, you also have platform management software. So these boxes, they have fans, they have thermal sensors, they have power supplies. The boxes get hot. The vendors create a thermal plan. The fans have to run at a certain speed based on a certain temperature. You don't want it to be super noisy all the time, so you don't want to run the fans at full speed. It's complicated. It's not that interesting, honestly. There's not a lot of room for innovation here, but it has to be done. So you have a whole bunch of just kind of table stakes behaviors that you need to implement. Make sure the box doesn't catch on fire. Make sure it's not too loud. Make sure that you can alert the user that one of the fans has failed, the PSU is not plugged in anymore. All of this network management, sysops kind of behaviors that have to do with making sure your equipment works properly and making sure that you can detect when your equipment is about to fail before it fails. And so none of this has anything to do with how you want your packets to operate in your network. Okay. In addition to that, you need operational status. Here's the inventory of the modules that are plugged in. Here's the, a lot of these things have status LEDs and things like that to tell you, like at a glance, whether things are working properly, even if you're not managing the. Is that a question? Sorry. Okay. So roughly, they all have to do the same thing. Sorry, I'm gonna get my time check here. So what's the problem with the problem in general? The problem in general with all of this is that all of those things are designed differently for different platforms. Hardware vendor says, if you go back to this list of things, the hardware, the person who makes the box, the vendor, Acton, EdgeCore, Quanta, Delta, all of these guys who build these boxes, and the same thing for companies that build the boxes for their own products, Cisco, Juniper, Extreme, all that. You have a variety of options. Can everybody hear me? Sorry, because I'm, okay. You have a variety of options, and you have to pick some subset of these things that are on the screen to create your box, right? You want something from Barefoot because you want it to have a certain set of behaviors. You want something from Broadcom. You like an x86 system because everybody likes that now, and you can afford it. Or you need an ARM32 integrated processor from Broadcom because you want the box to be cheap. You have a bunch of criteria that you need to satisfy to build a product, and some of those products are some of those criteria depends on what kind of speed you want to run the platform at. Is it a 10 gig platform, 40 gig, 100 gig, stuff like that. But in the end, the platform vendor has to make a selection of all of these components and then create something that works, okay? So the problem is they do that. Now, the whole reason that OCP has an acceptance process is because of all of these design decisions. Those design decisions have to be made, and then they have to be communicated, and they have to work, and they have to be reproducible. Because there's no one way to do it, and that's just how it is. So what used to happen is before all this open networking stuff got really hot and exciting, hopefully that's kind of why some of you are here, is the hardware platform and was designed by the same company that built the software. And so while all of this is true, all of the hardware could be different, could be designed differently for each generation, or even different products within the same product line. The hardware guys and the software guys work together to just understand how it works. So no problem there. If somebody needs to know, how is this connected to this over here on this box, they just send an email to somebody, or they go talk to their hardware team, or the hardware team does a training for the software guys, or they all collaborate, and basically the knowledge is available. So what's happening with open networking is that it's not true anymore. So if you want to build a network operating system that runs on open networking hardware, an operating system like Cumulus or Big Switch, PK8, any of these other guys, basically the open networking allows you to disaggregate the software development from the hardware development. Okay. But what that also means is it disaggregates your software developers from your hardware developers. So access to the information is sometimes difficult, or if the information and documentation is not clear, or if you don't understand the domain to begin with, it's very hard, right? And so this creates a problem where there's a barrier to entry for developing software for open networking. There's a barrier to entry to realize the goal of open networking, which is to democratize access to the hardware so that you can do things that you wouldn't have been able to do before, right? If you didn't, 10 years ago, if you didn't work for Cisco, or you didn't work for Juniper, or you didn't work for one of these companies, there was no way that you could build a switch. There was no way you could build software that would run on any of these boxes. There was no way that you could test, any ideas that you might have had. There's no way that you could learn how to do it. It's just impossible. Now, today, you can go to a website and you can have any of these boxes. They're going to cost some amount of money, but you can have any of these boxes delivered to your door. And that's actually a situation you just have not had for a long time. And so the next problem with that is what do you do with it, right? What do you do with it? It still takes a lot of knowledge, and it still takes a lot of effort. And so what used to happen is you would just build that effort and that knowledge within your own company, but now we don't have that because we're not all working for the same company, and the hardware is open, and we want the software to be open too. So how do we do that? First of all, I think it's important to realize that the things that you want to do in open networking, the things that you want access to when we democratize the networking hardware are not reading the fan speeds. It's not asking what the PSU input voltage is, right? These are all things that need to happen. You don't want to figure out how to make sure that the box doesn't catch on fire, right? What you want to do is access the data plane and do interesting things with the data plane or the control plane. So, As an end user, maybe this is hard, but as an end company that's doing open networking software, right? These are the things you're looking for. So if you have a fancy idea about how to, make BGP better or do a custom fabric or things like this, what you need is access to the switching and routing ASIC, right? Does anybody think that it's programming the fan controller on an Acton 7712 is super interesting? Raise your hand. Don't be shy. One guy, two guys. So, and if you're into that, that's fine. And there's this is all important, right? But for the most part, who's more interested in networking? Okay, so it seems like more people are interested in networking. So that's the whole point of Open Network Linux, okay? It's to solve all of the, what I'm gonna say, boring to NOS developers, not to this gentleman here. It's super important. Like I said before, this is all super important, right? You'll see later. I got a slide on it. But here are the things that are on these boxes that you have to understand before you can do anything at all with the box, for the most part, okay? Before you can get your first packet in and your first packet out, there's a bunch of stuff you have to understand about how to make the box work. Now, some of that stuff is covered by ONI, right? Like, how do I get the software on the box, right? All of this is basically designed to standardize the behaviors on these boxes that are created by multiple vendors that are designed to be used by third parties, right? They're not designed to be used by people that can talk to each other necessarily. They're not collaboratively designed. These are systems and standards put in place so that third parties can interact with this equipment and software, okay? So, who knows what a CPLD is? All right. Who likes programming them? Who likes the fact that the CPLD register set is different on every box you've ever seen? You do, sir? You like it? Right? This is a necessary piece of the box to make everything work, and I am not maligning any of these things. They're just not anything anybody likes to do, right? Except the guys who make them, and they try to make them, and they try to make sure that they have their own set of problems, right? Even making any of this stuff work at all, they have their own set of problems, right? Who knows what I squared C is? Who likes I squared C? Right? Okay. I squared C. If you don't know, I squared C is a low speed, low cost bus that allows cheap devices to talk to each other. Okay, and it's ubiquitous in networking because there's a lot of tiny little things you have to talk to, and you don't want that to be expensive. Okay, but it's actually very difficult. It's no end of practical problem for everybody. You'd rather get packets in and out of your box than figure out how I squared C works. Okay. Determine if a PSU has failed. Determine if the module has been plugged in, like these SFP modules, QSFPs, SFPs, if you know what they are, right? They are pluggable units. These are things, a class of things we call field replaceable units, or modular pluggables. So if you have a switch, you can plug in a SFP. You can have a copper cable. It can be a fiber. It can be a long reach, a short reach. So all of these different things, and the data center networking has evolved to support these as a concept because the costs and the choices for deploying them are wildly different. So the cost for fiber optic modules versus the cost for copper cable is very different. And only the person deploying the network knows what their use cases are. Only they are the one that know how far away their equipment is, what kind of other equipment they're going to connect it to, and stuff like that. So as a industry, we've decided that for data center networking, the connectivity choices will be separate from the actual switching hardware, right? But because of that, you have to write a lot of software to go figure out, did the user plug something in? What port did they plug it in at? What kind of module it is? What kind of layer 1 programming at my switch do I need to do based on the module that's plugged in? So on and on and on and on. Okay. Another thing that's kind of not interesting from the data plane perspective, but it's super important, are all of these modules have diagnostic information about their RX and TX light levels. If your network's not working, you need all of this stuff, right? But for the most part, can anybody tell me any MSA specification that determines how to read the RX light levels of a QSFP? No, right? No. That's fine. But it's not interesting. It's not interesting if you want to advance networking, right? Like I said before, the boring is also different. So it's not just different per vendor. It's different for every single platform. The CPLD is different. The way that the I2C tree works and the way the devices are connected, it's not hard. It's not necessarily complicated. It's just different, right? And if you don't know how different it is, or you can't accommodate the difference, or you can't even understand the difference because it's not documented, you can't use the box, okay? So remember how I said that they were different? This is where most of the difference is, right? Your box is going to be basically designed around one of the switching chipsets, Broadcom, Barefoot, Centec, Nefos, Marvell, right? All those ones that were listed before. The purpose of the box is to expose the functionality of that into your network, right? Either through programmability or through whatever fixed function that device has. The entire rest of the box is just life support for making that thing send packets in and out, right? So everything else is just different. How you access the SFP, what we call the SFP cages, how you get access to the device so they can get plugged into the bus so you can read and write them, how those things are wired into the switching ASIC itself, and then how you look at the thermal sensors, how you look at the PSUs, all of that stuff is just life support system for the switching device that's in that box. Unfortunately, all of the topology to talk to all of that life support system is just different all the time. So you might be an expert on how to program a Broadcom Tomahawk chip, but you won't be able to use that expertise until you go read Acton's document about how the I2C tree looks like on their box in order to get to one of the SFPs so that you can figure out whether it's a 100 gig long reach or a 100 gig short reach, okay? I know, it's very interesting. This is why I did this. Time check real quick. Last point. You can drown in the boring. Every single NOS provider has to do all this work, right? Even the platform vendor had to do this work just to make sure that it worked, right? Before they release the product, they have to go exercise all of these things. So in order to do it, they have to write software to go do it. So they'll have like a simpler version that's like a diagnostic kind of thing that's not like production ready and is not multi-threaded and not multi-processed and all of this stuff that you really need. But in the end, there's still some poor guy who's got to go do this also. So not only does the vendor have to do it, but Cumulus has to do it, Big Switch has to do it, everybody else has to do it. Like if you want to deploy a product based on one of these boxes, you have to write software specific to that box. Now, reading the fan controller on all of these open networking boxes is not something that Big Switch or Cumulus is going to compete on at a business level. This is not a thing that anybody wants to do more than once. And it's not a value add, it's not a competitive advantage, it's not anything but a waste of time. Okay? Which is why Open Network Linux exists. So you can drown in trying to get your I2C trees to work. You can drown in trying to debug why this particular module that's plugged in here doesn't work and whether it's a problem with the bus timing that you schedule for. Like there's just endless detail on debugging and working on these things. And if you've seen one, you don't ever want to see another one. You will wish they were all the same. So I'm sorry, is that a question? Yeah. Can we get you a microphone first?
I had a quick question. So how does this work differentiate from people who offer you turnkey solutions like Nutanix?
Can I answer that at the end? Because there's more stuff coming that will provide context for the answer. Okay? So everybody has to do this work. Like everybody has to figure out what temperature sensors to read and to figure out whether the box is getting too hot and which fans to turn on and turn off. And there's a enormous amount of work that the platform vendor does to do modeling and thermal modeling and imaging and testing and empiric measurements to figure out what fans need to run at what speeds in order to make sure this box stays cold, right? Heat is important. Like we're talking in data centers specifically, we're talking about a lot of physical metrics that you may or may not intersect in your technical life, right? Power consumption is super critical. Heat generation is super critical, right? Noise is probably the least interesting part, but they don't want it to be noisy. So there's a whole system of software that's needed to basically figure out, are you going to ruin your equipment, right? Has your equipment gotten so hot that if you let it continue running, you're going to ruin it? And the list prices for these, you're not going to pay this, right? But the list prices for these things are $30,000. Okay, so you don't want the box to melt itself down just because there was an error in the software, right? That didn't shut the box down or didn't adjust the fans properly to get the right cooling. Even if you don't melt down your box, you just start to have, you can have subtle network problems that just are really difficult to debug if you have physical integrity issues with your boxes. So you really you can't not do all of this stuff. And it's hard and it's annoying, okay? Does that make sense to everybody? Is there any questions about why that's important and why it would also not be that interesting to work on? Again, I'm trying to make it really clear that this is all super important to do, but everybody has to do it, and there's no innovation to be had, really. Plus, if everybody does it, there's a chance that one of us gets it wrong, right? Everybody has different kind of bugs. And so this is basically implementing state machines that were provided by the vendor, and those state machines can be verified. The vendor is the one that's most likely to know whether it's accurate or not. They're the most likely to know whether it's still accurate. So sometimes they revise the thermal plan after they've had some soak time on the boxes, right? And so maybe that doesn't make it out to Big Switch, that they had a critical error in one particular condition of the thermal plan, right? And so now, because Big Switch software is running and we wrote our own version of it, now the boxes are broken. So this is all immensely important stuff, but it only really needs to be done once. So if you've ever actually tried to make one of these things work, you might be able to identify with flipping over the entire conference table, punching the roof of your car a couple times on the way home, considering writing an app for your phone. So it is that irritating. Just take my word for it. If you've never worked on it, it is that irritating. So at some point, you just go, how can we do this better? Pull the keyboard out of the wall, sit down, take a breath, go like this a little bit. So what you need is, we need a standard environment that allows all of this stuff to be written once for two reasons. One, you don't want to do it. Nobody wants to do it. I don't want to do it. Nobody wants to do it, right? But it needs to be done. Second, even if you want to do it, it's a whole lot of work and a whole lot of time. And it doesn't get us anywhere, and it doesn't get you anywhere, because it doesn't get you any closer to testing out your new packet theory, right? It doesn't get you any closer to developing your product that requires networking behaviors, right? And so Open Network Linux is basically an environment and a system that allows you to get a starting point on all of these open networking boxes. And it allows you to get all of the code up front that you need to operate this box, to hide all of the differences, and get you a starting point that makes sense. It's kind of like if you just got a laptop from Dell and it had no software on it, right? Well, you got to go install Windows. You got to go, what if it doesn't have the right device drivers? What if it's got weird stuff on it, right? Same kind of thing. Nobody ever does that. There's no get a box and it doesn't have stuff on it anymore. So this is basically you need an environment that you can start from. And you need an environment that is, just like ONI, is collaborative, because the development of the boxes, of the hardware and the software, is disaggregated from the user. Right? So there's three people involved, right? There's the guy who made the platform, there's the guy who makes the software, and then there's the guy who wants to use the platform or write additional software on top of it, right? Sorry, just time check here real quick. I'm going to roll through this real quick. So Open Network Linux is basically the entire OS that you can run on the box minus the data plane. So minus access to the switching ASIC. This is all of the other stuff that you need to do. It has a serial port. You need to be able to talk to the serial port. It has a persistent storage device. It has all of these things. So if you look at basically just like ONI, right? Everybody who supports ONI is a subset supports Open Network Linux. So Open Network Linux is a reference base OS for OCP. So all of these companies, in addition to supporting ONI on their boxes, they also support Open Network Linux. And that means that if you buy one of those boxes or you access one of those boxes, and you can use Open Network Linux as the base for your operating system. It covers all the same kind of platforms from all of these vendors. 1 gig to 100 gig, stuff like that. So briefly, what ONL provides are all of the kernels that you need to run on all of these boxes, whether it's x86, ARM, PowerPC, whether it has a funky fan controller that you've never seen before. So basically, everything you need to make that box work in the kernel, we've configured it, and it's available. A standard user space. So the user space for all of these boxes for ONL is based on Debian for all of the architectures. And so if you like Debian, you'll understand what that means. If you've used Linux before, you can at least kind of approximate what that means. This is the thing that lets you run stuff. Okay. On top of that are the switch specific, sort of open networking specific stuff. So all of that stuff that I said was different, we write abstraction APIs for. There are APIs that allow you to ignore the fact that there are 7 I2C muxes on this box. Right? You just don't need to know any of that stuff. What happens is the vendor implements a standard API that is submitted to ONL as part of the support for the box, and you just use one API that works on every single box that's supported by ONL. You don't have to know. You don't have to read a single piece of documentation about how the hardware is built. Okay. All of the thermal management that we were talking about before, all of that platform management stuff you get for free because the vendor writes it. The vendor is the guy who designed it, and then the vendor is the one who has to provide it. And so ONL provides a framework in which the vendor provides the code that does all of the things that you need so that you don't need to write it. So if you think about a lot of the boxes that a lot of the larger scale boxes we have now have BMCs, and BMCs have the same problem. BMCs were basically invented to encapsulate the management of the platform so that the system software didn't need to understand it, right? And so if you have a platform that doesn't have a BMC, then the vendor writes the software that is the equivalent of the BMC. ONL provides basically all of the parsing for all of the, if you know what the SFF MSA is, so this is the specification for what QSFPs, SFPs, all of these things look like. So ONL provides all the common code for you to start with to go and parse all of those MSA modules, right? Again, it's not complicated. It's not rocket science. It's all defined. It's all specified and documented, but no one needs to write it more than once. So ONL provides you the core libraries for not only accessing that information, but then parsing, identifying, and making decisions based on it. There are other operational things like, Kurt was saying ONI has a way to upgrade ONI on the box, while ONL has a way to include the updaters for ONI for any given box that you can then upgrade that specific box. And so the vendor can provide the current ONI versions for the box, and you can do things like have upgrade steps and firmware management for the boxes. So these CPLDs, and these are all programmable logic devices. And they find bugs in them, and you need to be able to get your box updated. And so there's a way that we've all agreed on how to upgrade your box, and ONL facilitates that by delivering the upgrader of the firmware from the vendor to you. On top of all that, you need a way to interact with ONI to install on the box. And so ONL takes everything I just said and then wraps it all up into a way that allows you to install on any of the boxes that are supported. Just a quick note. So ONL is not just, like a concept, right? ONL is the base for my company's commercial products. So it's tested all of the time with our commercial products, with every platform on our HCL, and it's deployed in literally hundreds of different environments. So it's not a fork. We don't have a private version that really works. We build our software directly upon the open source repository for ONL. It's easy because I'm the gatekeeper for everything that goes in there. So in the end, ONL is basically the foundation for you to build a NOS. And so there's a lot of other things that we could talk about in the workshop about how you brand ONL for your own thing, or then how do you inherit all of the stuff from ONL and then add your own stuff on top, and how do you add your data plane stuff? And it's very similar to the way that we build our own commercial products for Big Switch. We use ONL as the base, and then we add special stuff on top. We rebrand it. It has all this infrastructure in place for you to do that. And we're not the only company that does it. And I'll be happy to explain to everybody during the workshop or at some other time if you don't attend the workshop on how to do that. But so what you get is you get a basic operating system that has access to everything, make sure the box works, and get access to all the peripherals. And then what platform vendors get is one vehicle to write the drivers for those platforms. And they only write it once, and then maybe twice if we're talking about Sonic. But they write it once or twice, and then that's how their code is delivered. And they also don't have to answer your email, right? Because they don't even have a guy who can answer your email, right? So in the breakout session, we'll talk about the ONL architecture, building, depending upon how many people show up and what your experience with ONL is and what your questions might be. We could, I've got a presentation that we can go through, or, I can sit with you, I can answer all your questions, whatever you like. If you want it, ONL is on GitHub on Open Compute, and you can see the web page for my company with the little blurb that I opened the presentation with, and that's it.